Albert Einstein, a giant of modern physics, was famous for his groundbreaking theories about gravity and the universe. His work reshaped our understanding of space and time. But even Einstein found some scientific ideas hard to swallow. Despite his genius, there were concepts that even he struggled to accept. One of them was the strange and perplexing world of quantum mechanics. This field of physics, which emerged in the early 20th century, deals with the behavior of the tiniest particles in the universe. These particles, smaller than atoms, behave in ways that defy our everyday understanding of reality. The rules governing their actions are bizarre and counterintuitive. What Einstein saw happening in the quantum realm deeply troubled him. He couldn't reconcile these strange behaviors with his own theories. He felt that the universe couldn't be that random or disconnected. The idea that particles could behave unpredictably was unsettling to him. At the heart of Einstein's discomfort was a phenomenon known as entanglement. This concept suggested that particles could be linked in a way that defied classical physics. Imagine two particles linked in a mysterious way. When you do something to one particle, the other reacts instantly, no matter how far apart they are. This instantaneous connection seemed impossible to Einstein. It suggested a level of communication that violated the known laws of physics. This idea of instant reaction across distances was something Einstein couldn't accept. It seemed to contradict his own theories. He famously called it spooky action at a distance. This term reflected his discomfort and skepticism about the phenomenon. It violated his deeply held belief that no information could travel faster than the speed of light. This principle was a cornerstone of his theory of relativity. Einstein believed there had to be a simpler explanation, something we weren't yet seeing. He thought there must be hidden variables that we hadn't discovered. He theorized that these hidden variables were controlling the strange behavior of particles, making the universe more predictable than it seemed. Despite his efforts, Einstein spent years trying to disprove the idea of entanglement. However, experiments repeatedly confirmed its existence, challenging his views and reshaping our understanding of the quantum world. Einstein's skepticism stemmed from his deep understanding of the universe and his relentless pursuit of truth. He had revolutionized physics with his groundbreaking theory of relativity, which changed our perception of space and time. This theory beautifully explained gravity as the bending of space and time, providing a new framework for understanding the cosmos. It worked flawlessly on the largest scales, describing the motion of planets, stars, and even galaxies with remarkable precision. However, the world of quantum mechanics operated by a completely different set of rules, often counterintuitive and strange. In this realm, particles like electrons could exist in multiple states simultaneously, defying classical logic. Their behavior was governed by principles of probability and uncertainty, encapsulated in Heisenberg's uncertainty principle. The conflict between these two fundamental theories, relativity and quantum mechanics, highlighted a profound and enduring mystery in physics. How could the universe operate so differently at its largest and smallest scales, from the vastness of galaxies to the minuteness of subatomic particles? Entanglement sat at the heart of this conflict, a baffling phenomenon that challenged our very understanding of reality and the interconnectedness of particles across vast distances. So what is entanglement really about? Imagine two tiny spinning coins flipping in perfect sync. You separate them by a large distance, but their spins remain connected. If one coin lands on heads, you instantly know the other landed on tails. That's the essence of entanglement. Two particles, once linked, share a special bond. Measuring the state of one instantly determines the state of the other, no matter how far apart they are. This connection isn't about some invisible force traveling between them, it's deeper than that. The entangled particles are considered part of a single system, sharing a single fate, even when separated by vast distances. Section 4, spooky action in everyday objects, not so fast. It's tempting to imagine everyday objects becoming entangled. Could we link two apples, for example, so that biting into one instantly reveals the other's taste? Unfortunately, entanglement is incredibly fragile. It only thrives in the microscopic world of atoms and photons. The larger an object, the more it interacts with its surroundings. These interactions disrupt the delicate entanglement like noise, drowning out a whisper. While we can't entangle apples or people, the fact that we can entangle even tiny particles opens up incredible possibilities. Section 5, the quantum revolution from lasers to teleportation. In this section, we delve into the fascinating world of quantum mechanics and its groundbreaking applications. Entanglement might seem like a bizarre quirk of the quantum world, but its implications are profound. This phenomenon, where particles become interconnected regardless of distance, is reshaping our understanding of reality. This spooky action, as Einstein called it, is driving a technological revolution. It's not just a theoretical curiosity, it's the backbone of many emerging technologies. One area where entanglement is making its mark is quantum computing. These computers leverage the unique properties of quantum mechanics to perform calculations at unprecedented speeds. Imagine computers so powerful they make today's machines look like abacuses. These quantum computers could solve complex problems in seconds that would take classical computers millennia. Entanglement allows for the creation of qubits, the building blocks of these future computers. Qubits can exist in multiple states simultaneously, vastly increasing computational power. Unlike bits, which can only be 0 or 1, qubits can be both at the same time thanks to superposition. This duality is what gives quantum computers their incredible potential. Entanglement also plays a crucial role in quantum cryptography. This field uses the principles of quantum mechanics to create secure communication channels. By encoding information in entangled particles, we can create unbreakable codes. These codes are so secure that any attempt to eavesdrop would be immediately detected. Any attempt to eavesdrop would disturb the entanglement, revealing the intrusion. This makes quantum cryptography a game changer for data security. And then there's quantum teleportation. This concept, often misunderstood, is not about beaming Captain Kirk around, but about instantly transferring quantum information between entangled particles. It's not about physical transportation, but about the instantaneous transfer of information. This could revolutionize how we communicate and share data. This mind-bending technology could revolutionize communication and data transfer in the future. The possibilities are endless, and we're just beginning to scratch the surface of what quantum mechanics can achieve. Section 6, a universe interconnected, the legacy of entanglement. Einstein might have been skeptical of entanglement, but his skepticism pushed science forward. It forced physicists to test and refine their theories. And the more we learn about entanglement, the more we realize how interconnected the universe truly is. Entanglement is no longer just a theoretical curiosity, it's a key to understanding the fundamental nature of reality. It's also a powerful tool that's shaping the future of technology in ways we are only beginning to imagine. The universe, it seems, is far stranger and more wondrous than we ever thought possible. If you enjoyed this exploration of quantum entanglement, please like, share, and subscribe to the Science and History Archives channel for more fascinating content.